To understand the nature of the atom in a deeper sense would require someone to make a discovery along different lines. And that someone was Professor J.J. Thomson, a disciple of Maxwell in the theory of electromagnetism, and, in his own right, a man determined to look into the internal nature of the atom and to discover how it worked. Others would later turn the cathode ray tube into TV and computer screens. But more significant in the long run, Thomson's experiments showed that the rays emanating from a heated cathode in an evacuated glass tube were electrically charged particles. Most important, those rays could be deflected by electric and magnetic fields, and no matter what matter was in the tube, they were always the same charged particles. Thomson saw that all atoms contain the same working parts, or in his words, corpuscles, which would become known as electrons. With those parts in mind, he developed what was called the plum pudding model. And more than an intellectual snack, it was a substantial explanation for line spectra of the elements. In Professor Thomson's theory, each atom consists of a large sphere of positive electric charge, with just enough negative electrons inside to balance the total charge and to make it neutral. This seemed a sensible idea, but it would soon fail a crucial test.
And other new methods, we are able to break up atoms in a great variety of ways.
Baron Ernest Rutherford, Nobel laureate and peer of the realm. He'd come from New Zealand to study physics at Cambridge, and he'd had the opportunity to work there under Professor Thomson.
To a definite law, like a radioactive element.
And by the time he spoke these words, he'd not only long since succeeded his mentor as director of the Cavendish Laboratory, Rutherford had become headmaster of the atom itself.
And has given us a much clearer understanding of the absolute...
Even before Rutherford began his experiments, it had been discovered that atoms could split themselves naturally and emit alpha-ray radioactivity.
And the progress of our knowledge...
So when he and his associates passed alpha rays through thin metal foils, their experiments went precisely as everyone would have predicted.
Nuclear chemistry, which is confirmed.
The rays seemed to slice through the metal as if it were a pudding, with very little resistance, and went straight along their course with hardly any deviation. But one fine day in scientific history, they noticed the unexpected. The most incredible event that has happened in my life, stated Rutherford after the fact. It was almost as incredible as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you. The incredible event was that rather than winging their way right through the foil, some of the alpha rays bounced back. Rutherford realized that contrary to Thomson's model, all the positive charge of the atom had to be concentrated within a tiny nucleus. That was because, with all the positive charge concentrated in a very small region, the electric force nearby would be large enough to repel, or at least deflect, an energetic alpha particle if one got close enough. In addition, if the nucleus had most of the mass of the atom, it could repel the occasional alpha particle without recoiling very much. These ideas led Rutherford in 1911 to propose a planetary model of the atom. According to Rutherford, the solar system and the invisible atom were almost mirror images of each other. Both obeyed nearly identical laws. In Rutherford's model, each atom had a heavy nucleus that was positively charged. His nucleus was surrounded by light negatively charged electrons that orbited like planets around the sun. But while the planets were bound together by the force of gravity, the atoms were held together by the force of electricity. Like a Greek goddess in the heavens, this was an idea of incredible beauty. And by the same token, it was too good to be true. For one reason, when electrons are accelerated, they radiate energy in the form of electromagnetic waves. But an electron in orbit would be constantly accelerating, always radiating energy, going round and round, the electron would fall into smaller and smaller orbits, radiating not spectral lines, but a continuous rainbow of colors. And finally, necessarily, it would collapse into the nucleus. Dr. Rutherford had obeyed the laws of Newton and Maxwell, and those very laws were the downfall of his model of a planetary atom. What was needed was an even bolder step, and the path would be lighted by a discovery about light that had been made just a few years earlier.